You know, we talk a lot about making high-quality products, but what does that word quality really mean? Is it as simple as just meeting a spec sheet, or is there something more to it, something revolutionary?
For years and years, manufacturing basically had this goalpost mentality, right? If a part falls within its specified limits, it's good. If it's outside, it's bad, end of story. But does that actually make sense? I mean, is a product that just barely scrapes by, right on the edge of failing, truly the same quality as one that hits the target dead on? This very question is what sparked a total revolution in how we look at engineering and quality.
And this slide really nails the difference. The traditional view is like a cliff. You're either safe on top, that's a pass, or you've fallen off the edge, which is a fail. But this new philosophy, the one pioneered by Dr. Junichi Taguchi, sees it completely differently. He said quality is much more like a smooth valley. The second you stray from the absolute bottom, that perfect target, you start to climb the sides, and a loss starts to build up. A loss that gets bigger and bigger the further you get from perfect.
So who was the person behind this radical new idea? Well, that would be Dr. Junichi Taguchi, a Japanese engineer and statistician who was about to completely flip the script on how the world thought about quality.
Taguchi came up with this pretty mind-blowing redefinition of quality. He said it's not about scrap or rework costs inside the factory. No, poor quality is a loss to society. Think about it. It includes the cost to the customer when a product breaks, their frustration, their wasted time. For Taguchi, quality wasn't just some engineering problem to be solved, it was a social and economic one.
Okay, but how do you measure something as big and abstract as loss to society? I mean, that sounds huge. Well, Taguchi didn't just leave it as a philosophy. He quantified it. And this brings us to the mathematical heart of his entire approach, the Taguchi loss function.
The quality loss function, or QLF for short, is the tool that turns this big idea of harm into a cold, hard number. It's a way to calculate the financial cost of not being perfect. It basically says that anytime a product's performance strays even a tiny bit from its target value, a financial loss is happening.
And this picture makes it so clear. You can just forget the old goalpost where anything inside the lines was considered 100% good. Taguchi's loss function is this parabola, this U-shaped curve. The very bottom of that curve, where there is zero loss, is right on the target. The moment you drift away in either direction, you start climbing that curve, and the financial loss just grows and grows, exponentially.
And here's the formula behind it. Don't worry, it's simpler than it looks. L is the financial loss we want to find. To get it, you take the actual value of your part, y, and subtract the perfect target value, which is tau. That little difference is your deviation. Then you square it, which is key, because that's what makes the loss grow so much faster the further you are from the target. Finally, you multiply it by k, which is just a constant that turns that deviation into a real dollar amount.
So having a way to measure loss is incredible, but how do you actually reduce it? How do you get closer to that target in the first place? This is where Taguchi championed a proactive tool that, had been around for a while, but he really pushed it to the forefront of quality improvement. It's called design of experiments, or DOE.
So what is design of experiments? Well, it's a super systematic and efficient way to figure out what really matters in a complex process. Instead of the old school way of testing one factor at a time, which is slow and often misses important interactions, DOE lets you study the effect of many variables all at once. It helps you pinpoint the critical things that are causing all the variation.
And this slide clears up a really important point. People often get DOE mixed up with something called Statistical Process Control, or SPC. Just think of it like this. DOE is proactive. It's the design phase. It's how you figure out which knobs to turn to get the best result. SPC, on the other hand, is reactive. It's the monitoring phase. Once you know which knobs matter, you use SPC to make sure they stay where they're supposed to be. DOE helps you write the perfect recipe. SPC helps you make sure you follow it every single time.
So Taguchi then took this powerful idea of DOE and really focused it into a methodology he called robust design. The goal wasn't just to hit a target in some perfect, sterile lab. No, the goal was to create products that could perform consistently out in the chaos of the real world.
So what is a robust design? It's a product or a process that just keeps on working, even when it's faced with noise factors. And noise is basically anything you can't control or, frankly, don't want to spend the money to control. We're talking about things like changes in temperature, humidity, normal machine wear, or even tiny differences in the raw materials you're using. A robust product is just naturally insensitive to all that noise.
Taguchi laid out this really logical three-stage process to get there. First up, system design. This is your basic invention, the initial prototype. Second, and this is the most important step, is parameter design. This is where you use design of experiments to find the best settings for the things you can control to make the product's performance stable against all that noise you can't control. And only then, as a last resort, do you move to tolerance design, which means spending more money on higher grade parts or tighter specs.
And this is really the core of Taguchi's genius right here, parameter design. Instead of trying to control every single source of variation, which is often impossible or just crazy expensive, you design the product to be naturally resistant to it. It's all about using the cheap, easy-to-control factors to cancel out the effects of the expensive, hard-to-control ones. It's just a beautiful, elegant engineering solution. Okay, this all sounds great in theory, but what does it actually look like in practice? How does this philosophy really translate to the bottom line? Let's take a look at a quick case study.
So, the challenge was pretty straightforward. A small plastic part in an engine carburetor called a butterfly had way too much variation in its performance, and this inconsistency was causing all sorts of problems down the line. The team decided, okay, let's apply Taguchi's methods and see what happens.
And the result? It's staggering. By using design of experiments to find the best settings and then plugging that reduction in variation into the quality loss function, the team calculated a potential savings of $370,000. And that's not a one-time thing. That's for every 10,000 engines they produced. That's the power of connecting smart engineering to real money. And that right there brings us to the ultimate legacy of Taguchi's work. It wasn't just about statistics or tweaking machines. It was about building a critical bridge between two very different worlds inside a business.
This quote just captures Taguchi's contribution perfectly. He built a bridge. You see, engineers speak in millimeters, volts, and PSI. That's the language of things. But management, they speak in dollars and cents, the language of money. The quality loss function is the universal translator. It shows in undeniable financial terms how much a small engineering improvement is actually worth.
So what's the big takeaway here? Well, Taguchi's legacy is really threefold. First, he made improving quality something you could actually justify on a balance sheet. Second, he gave engineers a framework to show the real financial impact of their work. And maybe most importantly, he shifted the entire focus of quality away from just catching defects at the end of the line to designing quality in from the very beginning. He called it moving from inline to offline quality control.
And that leaves us with one last thing to chew on. If every single deviation from a perfect target creates a loss, just think for a second about all the products and services in your life that aren't quite perfect, but are just within spec, or good enough. According to Taguchi, every single one of them represents a hidden cost, a hidden loss to all of us. The real question is, how much are we losing without even realizing it?